Hello, guys. So, lastly, we studied how vehicles can take turns in a circular motion, and the force required for this circular motion. That means there should be a centripetal force acting on the vehicle when it takes a turn, and this force is supplied by the friction on the wheels. And you know that we learned that in some cases when velocity equals to a certain value, if the centripetal forces required for this circular motion is equal to the friction force, the maximum or the limiting friction forces, the car or the vehicle can skid outward, right? So if even if the friction is sufficient enough for certain velocities, there can be tilting effect on the car. So we studied both of these. So to avoid such tilting effects, what they do is they bank the road, right? That means there is slight elevation, a slight inclination of the road, right? So in this case, we studied that the required centripetal force is supplied by the component, horizontal component of the normal force. If you look at this diagram, you can see this is an inclined plane with an inclination of alpha, and there's a moving vehicle here, and this is the weight acting on it, and this would be the normal reaction. I have denoted by capital N sub zero to represent this is our model, and we assume now we of course there's friction on the road, but for this case study we assume no friction force is needed. So what is the maximum velocity or the optimum velocity of the car that it should achieve without requiring any frictional forces, right? So the centripetal forces necessary for the circular motion is supplied by the component of the reactions alone. No frictional forces are needed. So let's derive that equation. Okay, so now here's the thing. This is N naught, the normal reaction force. Okay, so this is alpha. So the required centripetal force is supplied by the horizontal component of this normal force, that is N naught sine alpha. So no other forces are acting in the horizontal direction. So actually this is enough for the centripetal force required for the circular motion. So if we resolve horizontally, we could get N naught cos alpha is equal to mg, right? N naught cos alpha is equal to mg. This is very familiar equation here. Now, if we resolve horizontally in this direction, the required force, now suppose the car is moving at a velocity v, tangential velocity v, and this curve has a center somewhere around here, which is r distance away from the track. And to have a circular motion with the velocity v, there should be a centripetal force required for that. The centripetal force required for this particular motion is mv squared over r. This is the required force. And we're going to find now the whether this is enough. So what is the velocity, the design velocity for this component force, right? So n naught cos alpha, sorry, n naught here sine alpha. So n naught sine alpha is the only force acting in the horizontal direction. So we will find what is the optimum Right? What is the optimum velocity? The design velocity, so that it will not require any additional forces. The horizontal component alone will certify this motion, right? N naught sine alpha equals mv squared over r. Right. So if I divide these two, 1 or 2, 2 divided by 1 will give me tan alpha equal to v squared over rg. Tan alpha is equal to v squared over rg. We cannot change g, and for a specific design, r is consistent. The only thing we can, and also the alpha is it's the same as a design feature, and by these three design features, we can obtain the optimum velocity. So v squared must be rg tan alpha. If v squared is equal to this value, so v is equal to root rg tan alpha, then this vehicle can move in this circular path without requiring any additional forces. Right. So what does it tell us? Now it tells us that n naught sine alpha will result in an optimum velocity, it's a design velocity, which requires no frictional forces. Now, suppose the car will move at a greater speed than the optimum speed. So what will happen? If this is to move at a greater speed v, by looking at this formula, you can see that if v or the velocity were to increase, there should be a force, additional force to make that happen, right? That means v squared is proportional to the force. If v2 increase, then the force must increase too. That means the horizontal components of all the forces must be greater than the previous value. If the velocity were to decrease, then the horizontal component of all the forces must be less than this value. Why? The required force should be lowered, right? Therefore, the resultant force should be less than n naught sine alpha. Now, here's the thing. How we can get this? If friction is not present, then obviously this car will skid up or down, depending on the situation here. If the frictional forces are present, then this friction force will provide additional forces necessary to maintain this motion, right? So let's look at this again. Now, what will happen is that when velocity increases, there should be a corresponding change in the force. Additional forces are required. Now, if it were to maintain the same force, if no frictional forces are there, so to maintain that, to maintain the motion, now this is constant, so you cannot have any additional forces. If friction forces is not there, that means if V increases, R should increase as well. If V increases, there should be a corresponding change in R. So what will happen? Then the car will skid outside or skid up this plane. It will try to skid up this plane. So by doing that, the radius will also increase, and they will maintain this formula. Okay. So if velocity is lower than the design velocity, then what will happen? If this is lower, to maintain the same force without requiring any frictional forces, R must be decreased, right? R must be decreased. That means the car will move down, right? It will skid downwards along the plane. So that radius will decrease. Now, when velocity increases, what will happen? the R has to change. Now, if the car has to stay in the same path, there should be additional forces acting on this. So, what is the additional force? The additional force is the friction. So, if it tends to move up the inclined plane, there should be a force restricting that motion that is given by the frictional forces, which will be acting in this direction. Okay. So, when the velocity decreases than the optimum velocity or the design velocity, and also to maintain the car in the same track, the force must decrease, right? So what happens if now it will tend to move downward when the velocity decreases? It will tend to move downward because it needs to change the radius to maintain the same maintain the same track. Now, if it is tending downwards, there will be frictional forces acting this direction, right? Okay, that is what you need to know. Now we'll work out this problem, right? So this is the first case. The first case is when velocity is greater than v naught, right? When velocity is greater than v naught, there'll be a drift in this direction. Drift in this direction. The car will tend to drift in this direction. So there should be a forces opposing that drift. So there'll be frictional forces acting downwards, down the slope. Okay. Now these are the forces all acting on the vehicle at that moment. So let's resolve vertically. When you do that, N1 cos alpha minus Fu sine alpha minus mg equals 0. This means N1 cos alpha is equal to mg plus F sub mu sine alpha. Now, now you see why I used a different subscription here in one, because clearly this component now cos alpha did not change. It's the same thing. This is the only thing that has been changed. So in note, the last time the required force n naught cos alpha was equal equal to mg. Now in this case, n1 cos alpha is equal to mg plus another component. So obviously we have to change this subscript here. If I resolve horizontally, the required centripetal force is supplied by the component from this normal force and the component from this frictional force. So the components would be n1 sine alpha plus f mu cos alpha, which is equal to mv squared over r. So let me just call it v1, v sub 1, just to make a comparison. Now, if you look at these two equations, equation 1 and equation 2, if I take out n1 from both equations, then I have to multiply this 2 by cos alpha. Then this becomes n1 cos alpha sine alpha plus f mu cos squared alpha is equal to mv1 squared over r cos alpha. Right. So now n1 cos alpha is mg plus f mu sine alpha. Mg plus f mu sine alpha into sine alpha plus f mu cos squared alpha equals this. So notice here that the car should stay on the same track. So that's why R is present here like before. It's the same value, same R. Now from this we get mg sine alpha, and here we get f sub mu sine squared alpha. Here you have sub mu cos squared alpha. So when you combine these two, you get f mu m1 squared over r cos alpha. If I divide this by cos alpha, and I get mg tan alpha plus f mu sec alpha is equal to m1 squared over r. Right. Since v sub 1 is greater than v naught, you can see that for this motion, you only required, if I write it again, mg tan alpha equals mv naught squared over r. Compare these two. Earlier you had mg tan alpha supplying the centripetal force necessary for this motion. Now you have mg, in addition to mg tan alpha, you have another force component which is supplied by the frictional forces, right? Okay, so let's look at the case 2 here. Now when v naught, let's say v sub 2 is less than v naught. Now if the velocity of the vehicle is less than the design velocity, so what will happen? It will try to drift in this direction, right? It will try to drift in this direction because it needs to change r in order to maintain the same, maintain the circular motion at that speed. Now what happens when it tends in this direction? So there'll be friction forces acting up the slope like this, f sub mu. And now if we resolve this vertically, we get into cos alpha plus f mu sine alpha equals mg. Now what happens? Into cos alpha equals mg minus f mu sine alpha. Okay. So earlier it was equal to mg, and in this first case, when the frictional force is acting, the normal force is equal to mg plus an additional force. And in this case, normal force, or the component of the normal force, is equal to mg minus the component of the frictional force, right? Now, if I resolve it horizontally, then the forces acting horizontal would be N2 sine alpha in this direction, and there'll be f mu cos alpha, acting in the other direction. So N2 sine alpha minus f mu cos alpha is equal to mv2 squared over r. We are assuming that the car stays on the same track. Now, if I get rid of this N2 from this equation, so what we get? We get the same result, but with the minus sign here. So let me just write down the answer. So finally, you should get mg tan alpha minus f mu sec alpha equals mv2 squared over r. Okay, so if I want, I can divide this whole thing by mg, then I get tan alpha equal to mf mu over mg sec alpha equals to v2 squared over gr. If you want, you can do this. Right. So that's about it for this example. This is a model. So what we have studied here is that a vehicle can move in a circular path without requiring any additional forces like frictional forces. If the road is banked, it can move in a circular motion without requiring any frictional force, right? So the centripetal force will be supplied by the horizontal component of the normal force. If the velocity is greater than the design velocity, what will happen? There will be a drift in this direction. There will be a drift in this direction. So to keep the car in the same track, there must be frictional forces acting in this direction. So there will be a component from the frictional forces acting towards the center of this circular path. So this will also come into play in addition to the horizontal component of the normal force. Okay, so both of them will assess the motion. What happens in this case when the velocity is less than the design velocity? The car will tend to drift in this direction down the slope. To restrain that motion, frictional forces are acting in this direction. Now, the resultant force towards the center would be N2 sine alpha minus the component from the frictional forces. And we finally arrived at this answer. Right. So thank you for watching this, and we'll discuss more example next week.